Next, I'll show you the model that I used. This is the Hamiltonian of the coexistent state. It is comprised of the paramagnetic part, the spin density wave interaction, and the superconducting parts. For cuprates, we use the one-band model to describe the Fermi surface. Epsilon is the bare electron energy in normal state in a square lattice. We can plot the Fermi surface by setting epsilon equal to 0. Epsilon is the green line in this figure. The mean field approach is to start with the pure spin density wave state, which means we have only the first two terms. We can decouple the four electron operators by using the definition of the spin density wave order parameter, which is expressed as W0. Once we diagonalize the first two terms, we will get two quasi-particle energies. I call E alpha and E beta. Now I can plot Fermi surfaces according to E alpha and E beta, and I get a plot like this. The blue line is the beta band or hole pockets. The red one is the electron pockets. It can be seen that the introduction of the spin density wave term changes the Fermi surface. The original band splits into an alpha and a beta band. The shape of the band changes with W0, which is the order parameter of the spin density waves. From these plots, you can clearly see that when W0 is increasing, the size of the pockets becomes smaller and smaller. Between mu equal to 0.7 and 0.8, there is a Lipschitz transition. The spin density wave order parameter not only splits the band under normal state, it also changes the size of the pockets. Next, I will show you some of the calculation I have done for the cuprate system. After the spin density wave transformation of Hamiltonian, we will get diagonal terms with quasi-particle energy, E alpha and E beta, and off-diagonal terms, which are the superconducting gap functions. Using the BCS gap function of the electron pair, we can get a self-consistent gap function for delta alpha and delta beta. These two gaps are coupled to each other and with multiple terms. However, we can calculate them numerically. If you look carefully, you can see that the superconducting term is a little different from the ordinary superconducting pair term. We have spin up down and up down here instead of up and down. That's because the superconductivity is mediated by the spin flip channel. If this is a non-spin flip channel, if this is a non-spin flip term, there will be a sign difference in the middle term of N and F. This will cause a problem in the gap calculation that I will discuss later. We have a general gap function now, and we can plug in different symmetries for the interaction strength and see what the effect will be. We will look at the asymmetry and the D-wave symmetry interactions. The interaction for the interaction for S-wave symmetry is a constant. After plug Vs in the gap function, we get unconventional S-wave gap function for alpha band and beta band. This is due to the spin density wave coherence factor U squared minus V squared. At these points on the Fermi surface, the gap functions are zero. The gap size doesn't depend on whether the superconducting pairing is from the spin flip channel or the non-spin flip channel. If we look at the generalized gap function, the energy, the interaction strengths have the same sign because it's a constant. And then so VFUV minus VFVU will cancel the middle term of the F, and it's the same thing for N. So we want the sign of the middle term of N and F doesn't affect the S gap result. But for the D-wave case, the interaction for D-wave symmetry has this form. You can see when there is a pi difference in the cosine function, we will get a sign change. This will give us a prefactor of 4 in the UK, VK, UPVP term. This results in a sign difference in delta 1. And how does this affect the gaps functions? We anticipate that when spin density wave comes into a superconducting state, it will either enhance the superconductivity or jeopardize the superconductivity or do nothing. According to the numerical results, the non-spin flip channel will enhance the superconducting gap. This is not the same physical result that was observed in the Kullbaum phase diagram. The spin flip channel seems to be the right mechanics in the coexistent state. What I have here is the gap result from the spin flip interaction. The gap size of delta 0 is decreasing with W0, and delta 1 will increase with W0 due to the coherence factor UKVK. At the same time, delta 1 is proportional to delta 0. So when delta 0 decreases rapidly, the size of delta 1 goes down as well. Finally, at the critical point of W0, they both become 0. This figure shows the angular variation of the gap along the Fermi surface. The distance between alpha band and beta band widens when W0 is large. When W0 is small, the gap symmetry is more like an ordinary D-wave symmetry. And when W0 is large, the gap size on the edge of the electron pocket decreases while the gap on the beta band edge goes up. The nose of the gap happens only on the center of the beta band, which is the 45-degree position. I also calculate the vector susceptibility. In Ismer's paper, it says the non-spin flip channel, which is the longitudinal spin mode, is gapped in the spin density wave state. So I calculated the spin susceptibility. Here I don't find a gap in the ZZ components. However, the susceptibility in the transverse mode is twice the one in the longitudinal mode. We can conclude that the spin flip interaction is stronger in the spin density wave state. And from the spin operator, you can see mx is related to the mixing of the spin up and spin down electrons. Next, I calculate the superfluid density in the coexistent state. Superfluid density is the inverse of the penetration depth square. The penetration depth is a common measurement of superconducting properties. Therefore, once we have superfluid density, we can compare with experimental data. Superfluid density has a diamagnetic and paramagnetic response. Again, I converted them in terms of creation and annihilation operators and performed the Bogoliubov transformation. We get an expression like this, so we can calculate them numerically. The superfluid density is quite linear with W0. Around the critical point of W0, when W0 is much larger than the superconducting gap, the superfluid density decreases quite rapidly around this point.